Did you know we've explored less than 5% of the ocean? Picture plunging into endless blackness where water presses down like 1,000 elephants. Yet life not only exists here, it flourishes in impossible ways. Down here, fish glow with their own light, jellyfish grow longer than buses, and creatures survive without sunlight for millennia. The deep isn't just empty space. It's an alien world where evolution has crafted solutions we're only beginning to understand. Every descent reveals new mysteries, like why some species live for centuries, or how entire ecosystems thrive near boiling thermal vents. What other secrets might the darkness hold? The sunlight zone, a world of familiar strangers. The sunlight zone extends from the ocean surface down to 200 meters deep. While this layer receives the most sunlight and appears familiar, it contains marine life that challenges our expectations. This zone accounts for only 5% of the ocean's total volume, yet houses the majority of the sea's visible biodiversity, a bustling metropolis of life where most species remain unknown to us. Take plankton as an example. These microscopic powerhouses produce more oxygen than all rainforests combined. Many species also exhibit bioluminescence, like the dinoflagellates that create glowing blue waves at night. Some jellyfish use this light to attract prey, while others employ it as a burglar alarm, triggering bright flashes to reveal smaller predators to larger ones. These tiny organisms form the foundation for ecosystems that stretch far beyond their size. Coral reefs function like underwater megacities, covering less than 1% of the ocean floor, yet supporting 25% of marine species. Each polyp in a coral colony partners with microscopic algae, exchanging shelter for food through photosynthesis, a delicate balance that sustains extraordinary biodiversity. But this vibrant world also hosts ruthless predators. The lionfish, armed with venomous spines, can decimate reef fish populations by nearly 80% in just 5 weeks. Meanwhile, the trumpetfish hunts through deception, swimming vertically to blend in with coral before striking sideways at unsuspecting prey. These intricate relationships showcase nature's brilliance and fragility in equal measure. One paradox of the sunlight zone is that the same currents nourishing life can also spread danger. The Portuguese man o' war drifts across the surface like a ghost ship, trailing venomous tentacles up to 30 meters long. Its sting kills fish instantly and leaves painful welts on humans. Yet in this same water, clownfish dance safely among sea anemones, their protective mucus coating making them immune to stings that would kill others. Below the shimmering surface, schools of sardines perform balletic maneuvers to evade predators. A single misstep could trigger a feeding frenzy. Some sardines see polarized light, a vision beyond human capability to spot threats. Nearby, archerfish demonstrate another survival tactic, spitting precise water jets to knock insects into the water from overhanging branches. Survival strategies intensify near the zone's lower boundary, where sunlight fades around 150 meters. Here, lanternfish, among Earth's most abundant vertebrates, conduct nightly vertical migrations. They rise near the surface to feed under darkness, then retreat by day to avoid predators. Their bodies contain light-producing organs that mask their silhouettes from hunters below, perfectly matching the fading sunlight. Even common fish display extraordinary adaptations. Flying fish launch themselves 50 meters through air at 60 kilometers per hour, gliding on wing-like fins to escape predators. Deeper in this zone, elusive giants like the oarfish grow beyond 8 meters. So rarely seen, they inspired sea serpent legends. But at 200 meters, everything shifts. The warm blues give way to Twilight, where creatures evolve solutions to problems unknown elsewhere. Here, light becomes both scarce resource and deadly weapon. Mastering it means survival in a world where every advantage counts. The Twilight Zone, where light becomes a weapon. The Twilight Zone begins where sunlight weakens to near darkness, between 200 and 1,000 meters deep. This layer contains the largest animal migration on Earth. Hundreds of species rise to feed near the surface each night and sink back down at dawn. About 90% of Twilight Zone species produce their own light through bioluminescence, using it to hunt, hide, and communicate in ways surface creatures never could. The vampire squid demonstrates one of the strangest defenses in this zone. When threatened, it releases a sticky cloud of bioluminescent mucus that glows blue for nearly 10 minutes, like a smoke screen of light that leaves predators snapping at empty water. This species also flips its body inside out, covering itself with a spiny, webbed cloak when danger approaches. Unlike true squid, it drifts slowly to conserve energy in an environment where meals are scarce. Predators here master the art of invisibility through counterillumination, nature's version of active camouflage. Many fish and squid grow light-producing organs on their undersides that precisely match the faint glow from above, erasing their silhouette when viewed from below. The stoplight loosejaw takes this further by producing red light invisible to most deep-sea eyes, giving it a private hunting spotlight. The hatchetfish perfects disappearing axe with a two-part strategy. Its flattened body reflects ambient light so efficiently it nearly vanishes when seen from below, while downward-facing bioluminescent spots complete the illusion. Some species add transparent skin to this tactic, letting light pass straight through their bodies like living glass. Prey animals weaponize light as deception. The cookie-cutter shark lures larger predators with a glowing belly, then takes circular bites from their flesh using suction-like lips and rotating teeth. Deep-sea shrimp eject bioluminescent fluid like underwater fireworks, confusing attackers while they escape. One squid species detaches its own glowing arm as a decoy, the disembodied limb twitching and flashing while the squid jets away. Every night, the Twilight Zone stages the planet's greatest elevator ride. Organisms like lanternfish and krill swim hundreds of meters upward to feed, returning to depth by dawn in a migration so massive it sometimes fools sonar into detecting false seafloors. This nightly tumble of billions of organisms acts as a biological conveyor belt, transporting carbon to deeper waters, where it influences global climate patterns. The zone contains the ocean's largest known population of vertebrates. The bristlemouth, a small bioluminescent fish, likely numbers in the hundreds of trillions, making it one of Earth's most abundant vertebrates. Yet predators like the saber-toothed fish evolved needle-like backward-angled teeth that trap struggling prey like fishhooks. Pressure here becomes crushing. At 1,000 meters depth, every square centimeter withstands about 100 kilograms of force. Deep-sea proteins contain molecular reinforcements to avoid denaturing, and some fish replace gas-filled swim bladders with water to avoid implosion. As sunlight fades completely around 800 meters, many species grow unusually large, a phenomenon called deep-sea gigantism. The giant ostracod, a crustacean, reaches sizes 20 times bigger than its shallow water cousins, likely because larger bodies conserve energy in the cold, dense water. Deeper still, where no light penetrates, life faces even stranger challenges. The Midnight Zone, life in permanent darkness. The Midnight Zone begins at 1,000 meters deep, where sunlight never reaches and pressure exceeds 100 atmospheres. Most species here evolved without ever experiencing daylight. Their world exists in permanent darkness illuminated only by biological light. Anglerfish demonstrate one of nature's most extreme reproductive strategies. A male, barely larger than a human finger, locates a female through pheromones in the vast darkness. Upon contact, he bites into her skin, releasing enzymes that fuse their circulatory systems permanently. The male degenerates into a parasitic sperm sac. Some females carry up to 8 mates simultaneously. This ensures reproduction in an environment where encounters prove vanishingly rare. Gigantism appears commonly here. The giant squid exceeds 13 meters in length with eyes the size of dinner plates, the largest of any animal. These massive eyes detect faint bioluminescent signals across great distances. The colossal squid grows even heavier, equipped with rotating hooks in its tentacles that function like serrated blades. At 4,000 meters, pressure equals 400 kilograms per square centimeter, enough to crush a human lung to soda can size. Grenadier fish adapt with flexible cartilage and pressure-resistant blood proteins. Their bodies withstand forces that would implode most submarines. The black dragonfish wields a unique advantage. It produces and sees red light like a submarine beacon in the void. Most deep-sea creatures detect only blue wavelengths, making the dragonfish's crimson glow invisible to prey. Its jaws unhinge to swallow victims larger than itself, while transparent teeth camouflage its outline when closed. Food scarcity drives extreme adaptations. The swallower eel's stomach stretches like biological rubber to engulf prey 3 times its size. The tripod fish perches on elongated fins, using pelvic fin antennae to detect microscopic water movements from drifting organisms. Bizarre symbioses thrive here. The vent octopus partners with bacteria that convert toxic hydrogen sulfide into energy. The microbes colonize specialized gills, feeding their host in exchange for shelter. Similar relationships occur between tube worms and sulfur-processing microbes at hydrothermal vents. Scientists estimate 95% of this zone remains unexplored. Up to 30% of collected specimens represent unknown species. Many disintegrate during ascent, their bodies decompressing into gelatinous masses before reaching the surface. At 3,000 meters, the Dumbo octopus drifts just above the seafloor, using sensitive arm tips to detect crustaceans hidden in sediment. Meanwhile, the pelican eel's jaw opens wider than its body, funneling prey into an expandable stomach resembling a pelican's pouch. Its bioluminescent tail pulses red, a color invisible to most predators. Transparency serves as camouflage for creatures like the glass squid. Its entire body remains see-through except for the digestive gland and eyes, which are masked by reflective tissues to avoid detection from below. Some species supplement this with counter-illumination, mimicking faint sunlight from above. Pressure-resistant bacteria dominate here. Certain strains survive compression, exceeding 1,000 atmospheres using reinforced cell membranes. Their DNA repair mechanisms are now studied for potential medical applications. The midnight zone gradually transitions into the abyssal plain below 4,000 meters, where conditions grow even more extreme. Yet the ocean floor plunges another 6,000 meters deeper, a realm requiring adaptations beyond even these hardened survivors. The abyssal zone, crushing pressure, thriving life. The abyssal zone starts at 4,000 meters deep, where pressure exceeds 400 times surface levels and temperatures hover just above freezing. This vast plain covers more than half the planet's surface, yet remains one of the least explored regions on Earth. Only about 1% of organic matter from surface waters reaches these depths, mostly as slow-falling marine snow composed of dead plankton, fecal pellets, and other biological debris. Hagfish dominate the abyssal seafloor as opportunistic scavengers. They release slime from 100 glands along their bodies when threatened, producing enough mucus to turn 100 liters of water into gel within minutes. The slime's microscopic fibers expand rapidly in seawater, choking predators' gills. Hagfish feed by penetrating dead animals through natural openings, consuming them from the inside out while absorbing nutrients through their skin. Chemosynthetic ecosystems thrive around methane seeps, where tube worms like Riftia pachyptila grow over 2 meters long. Their red plumes contain specialized hemoglobin that transports both oxygen and hydrogen sulfide. Clams and mussels here host symbiotic bacteria that oxidize methane. 1 square meter of seep supports 10 times more biomass than surrounding sediments. Deep-sea fish adapt with pressure-resistant protein structures. The Hadal snailfish thrives at 6,000 meters with a cartilage framework and gelatinous body that resists compression. Standard swim bladders would collapse instantly. Most materials behave differently under such pressure. Aluminum becomes brittle, rubber coatings flow away from compressed areas, and even Teflon develops conductivity issues. Submersibles require titanium or syntactic foam to withstand abyssal conditions. The Titan's 2023 implosion at 3,800 meters revealed carbon fiber's limitations. Standard steel hulls visibly compress at these depths. Only 7 manned vehicles can reach full abyssal zones, all with limited operational windows before maintenance. Sea cucumbers process 90% of organic material reaching the seafloor. Some species, like Peniagone, leave distinctive trails as they walk using water-filled tube feet. Their specialized enzymes break down wood from surface events. Some can even regurgitate and regrow their entire digestive system as defense. Fall events create temporary ecosystems when large food sources arrive. A single whale carcass provides more nutrients than decades of marine snow. Ostax worms dissolve bones with root-like tendrils, while amphipod densities spike to 4,000 per square meter, 40 times normal levels. These communities can persist for 50 years. Manganese nodules grow 1 millimeter per million years. A 1978 discovery in the Clarion-Clipperton Zone revealed nodules rich in cobalt and nickel, commercially valuable but ecologically destructive to mine. Tests show sediment plumes from harvesting can smother filter feeders 10 kilometers away. Pressure experiments reveal surprising effects. Styrofoam cups shrink to thimble size at 4,500 meters, and wood's air pockets implode, preserving 8,000-year-old trunks with intact bark. Microbes here metabolize 100 times slower than surface bacteria. Some take a decade to divide, offering insights for astrobiology. Bioluminescent flashes from fish like the Abyssal grenadier pierce the darkness, likely serving as communication. Some species may sense their environment through weak electrical fields, taking advantage of water's high conductivity under pressure. The zone gradually transitions into the hadal zone below 6,000 meters, where even robust bacteria enter stasis until tectonic activity stirs nutrients. The final frontier lies even deeper. The hadal zone, Earth's most alien landscape. The hadal zone begins where the abyssal plain drops into trenches below 6,000 meters, doorways to a world more alien than most sci-fi landscapes. These trenches form where tectonic plates collide, creating the planet's most extreme environments. When the DSV Trieste made its historic 1960 descent to Challenger Deep, the crew reported cracks in their viewing window from the immense pressure, a reminder that fewer people have visited this zone than walked on the moon. Here, geology shapes life in extraordinary ways. Subduction zones push organic-rich sediment deep into trenches, while hydrothermal vents release 450 degrees Celsius water that supports entire ecosystems. The Chromatic Trench near New Zealand contains vents hosting specialized snailfish whose proteins stabilize against both extreme pressure and heat. Adaptations found nowhere else on Earth. The hadal zone's inhabitants defy expectations. Amphipods grow to 34 centimeters long, 10 times larger than shallow water relatives, with aluminum-reinforced exoskeletons that withstand pressures equivalent to 1,800 elephants on a single square meter. Microbial life dominates, with trench sediments containing 100 times more bacteria than nearby abyssal plains. Some species take 1,000 years to divide once, surviving complete nutrient deprivation by entering suspended animation. Pressure transforms materials unpredictably here. An aluminum sphere would compress nearly 7% at 10,000 meters, becoming brittle enough to shatter from minor impacts. Submersibles require titanium alloys or ceramic composites. Steel bends permanently under hadal pressures. Even sound behaves strangely. Underwater gliders mapping the Serena Deep recorded echoes, suggesting undiscovered geological formations. The Mariana Trench reveals nature's ingenuity. Its deepest known fish, Pseudoliparus swirii, filmed at 8,178 meters, has a skull with pressure equalizing gaps and produces antifreeze proteins. Researchers estimate hadal fish may live 30% longer than shallow water counterparts due to slow metabolisms in the frigid darkness. Deep sea currents breathe life into these depths. The Denmark Strait Cataract plunges cold water 3,500 meters down with force equal to 200 Amazon rivers, transporting oxygen that prevents trenches from becoming lifeless. Some trenches receive centuries' worth of sediment in single events. The Japan Trench recorded 25 centimeters of deposition after the 2011 tsunami. Exploring this realm pushes technology to its limits. The DSV limiting factor, currently the only manned vehicle rated for 11,000 meters, requires 90 days of maintenance between dives. Hadal mapping progresses slowly. Modern sonar struggles with steep trench walls, leaving potential undiscovered canyons deeper than currently measured. Hadal life holds medical promise. Trench bacteria produce enzymes stable under extreme pressure, useful for high-temperature industrial processes. Fish cartilage-strengthening compounds might treat human joint disorders. Yet 85% of hadal organisms likely remain undiscovered. Each dive reveals new species. These trenches may even hint at extraterrestrial life. Jupiter's moon Europa has subsurface oceans 10 times deeper than Earth's trenches. Bacteria from the Atacama Trench survive without sunlight by processing inorganic compounds. Similar organisms could persist in alien oceans. Despite its isolation, the hadal zone connects to surface ecosystems. Isotopic analysis shows trench organisms incorporate carbon from phytoplankton blooms. Even microplastics now contaminate these depths. Pet fibers found in Mariana Trench amphipods prove human pollution reaches Earth's most remote environments. Current research targets unexplored trenches like the Philippine and Tonga trenches, each potentially hosting unique species. The New Britain Trench contains thermal vent communities unlike any others, while the Java Trench's shape creates current patterns that may support unknown filter feeders. This hostile world, barely explored, holds secrets to life's origins and limits. Bioluminescence, nature's deep-sea lanterns. In the ocean's depths where sunlight never penetrates, 76% of species create their own light, a survival necessity in this eternal night where darkness would otherwise mean isolation and vulnerability. This bioluminescence forms a complex visual language, with blue being the dominant color since it travels farthest underwater. Yet some species evolved specialized exceptions to this rule. The stoplight loosejaw wields an evolutionary advantage, red bioluminescence. While most deep-sea creatures lost red vision long ago, this predator developed both red light production and detection. Its subocular photophore acts like a sniper scope, emitting an invisible beam to spot prey before switching to blue for the attack. Dragonfish enhance this strategy with multiple light organs, red for stealthy hunting and blue for interspecies communication. Symbiotic relationships power many of these light systems. Flashlight fish harbor glowing Vibrio bacteria in cheek pouches, controlling illumination with eyelid-like membranes to coordinate group hunting. Squid weaponize these bacteria differently, ejecting them as glowing smoke screens while maintaining fresh cultures in specialized organs. Color carries specific meaning in the deep. Sparkling Inope squid display unique blue photophore patterns akin to fingerprints. Vampire squid release bioluminescent particle clouds to disorient threats. Black devil anglerfish alternate between blue lures for prey and red signals for mates, a private channel most species can perceive. Camouflage reaches remarkable sophistication here. Firefly squid adjust their ventral glow to match changing light conditions during daily migrations. Some species precisely mimic moonlight patterns through wave-like photophore sequences, vanishing against the faint surface glow. Predators employ light as a weapon. Hatchetfish activate belly photophores to create confusing multiple images. Gulper eels flash white oral lights to stun prey mid-strike. Cookie cutter sharks disguise themselves with a glowing collar, luring fish into thinking they've found food rather than becoming it. Defensive bioluminescence proves equally inventive. Atala jellyfish trigger rapid blue flashes. A burglar alarm summoning larger predators against attackers. Comb jellies scatter rainbow-like light to overwhelm pursuer senses. Brittle stars sacrifice glowing limbs that continue flashing as decoys for hours after detachment. Communication follows precise protocols. Male ostracods trace species-specific light patterns to court mates, with females responding in coded sequences. Squid exchange threat displays through alternating flash rhythms, duration, and frequency conveying different warning levels. The deepest known bioluminescence challenges pressure limits. Mariana Trench amphipods glow steadily from leg photophores, likely for recognition in absolute darkness. Their chemistry differs from shallower species, adapted to function under crushing forces. Recent expeditions documented unidentified jellyfish pulsing green at 9,000 meters, breaking previous depth records. Human applications emerge from these adaptations. Glowing plankton chemicals now help surgeons highlight brain tumors. Engineers study firefly shrimp photophores to design more efficient LEDs. Military researchers explore counterlumination principles for stealth technology, while marine biologists deploy robotic bioluminescent lures to study elusive species. Some capabilities hint at undiscovered complexity.